First of all, I would like to thank QUT Bluebox for organizing this fantastic workshop and giving me an opportunity to share my experience with all of you. So in 2009, I joined QUT to start my PhD, and the main motivation of doing PhD in Australia was cricket, to be honest. And so I got my PhD, and I should acknowledge the cricket for my achievement. So I just want to explain you those steps, like how I got from basic research to the commercialization. Like these are the steps. So the first thing was definitely when I started my PhD in 2009. It was a very basic research. I had no idea about the commercialization or there will be any product from my PhD or from my research. So I started with my basic research, and in the final year of my PhD, at the end of my third experiment, I came up with a novel idea of the design of a spectacle, and I thought it might be useful to treat myopia or nearsightedness. I will definitely explain and define the myopia later on, but I don't want to talk about the science too much. So after that, I proposed this idea to my supervisors. I had two supervisors, principal supervisor and associate supervisor. So when I approached idea to the supervisors, they were quite excited with the ideas, but then one of the supervisors said to me, it is a good idea, but you have to find out that it has not been done by any other people. So that's the key thing. So then I started searching the different literature, papers, and the patent. And in 2 weeks' time, I found there are definitely a lot of related work have been done, but there was not exactly the idea was not exactly the same with the previous work. Then I said to my supervisor, so I have done some research and I found this is a novel idea. So what do we do? Then my supervisor said, okay, let's approach to the bluebox. So then I made a proposal. I made a PowerPoint presentation with some background information about the myopia, about my research results, and the application, what would be the novel idea. And then after 1 week time, I think bluebox took 1 week time, and then they came back to us, and that was quite exciting news. We organized a meeting. I think that time Dennis Hodge, she was actually looking after my application. And we had a meeting, and she said, well, bluebox is quite interested about your research topic, and it is interesting area. It is quite demanding area right now, the myopia, so we should go ahead with your idea. But at that time, still, we didn't know that the idea is novel or not. So what we did after that, we have sent our idea to a patent attorney. He was in Melbourne. So with the idea and all the related patent and the papers. And then he has done the evaluation on our application, and then he has sent actually a report. And the final comment was the idea is novel, but there might be some question about the obviousness. So when I was going through that report, so I was a bit confused. And then I went to my supervisor and said, I don't understand this thing very well, because it says it's a novel idea, but there is a question of the obviousness. What does it mean? Then my supervisor says, don't worry about it. It's not like science. Science might have a definite answer, yes or no, but IP is always a gray area. It's in between white and black. It's not always yes or no. So that was quite interesting to me. Then definitely bluebox was actually very helpful, and they organized another meeting, and they said, okay, this is a very good approachable idea. We should go ahead with the patent application. And in that report, the patent attorney, he also mentioned that we had to perform another experiment to prove our concept, prove our hypothesis. So we had to conduct another experiment. But at that time, bluebox decided to apply for a provisional patent application. And after the provisional patent application, we had 1 year time for the final patent application. So during that 1 year time, I conducted that experiment to prove our hypothesis. So that was the proof of concept experiment I have done. And the data actually was looking quite promising, and it proved our hypothesis. Then bluebox decided to launch the final patent application, what we have done in 2012. So we are standing in between these two steps right now. We haven't reached the final step. So right now what we are doing, the patent application is still under examination, and so we are actually trying to communicate with the different companies, different industrial partners, and I should say that definitely bluebox is the leading. They are actually communicating with the different industry and like different spectacle companies. A couple of them are quite interested about our technique. So there might be some collaboration in future, and we might have some funding, and then we can conduct more experiment for the further development. And then once we have the product, the final glass, it's a quite complex design. I'll go through all the design one by one. And it's a quite complex design. Once we have the final design, then we can send that spectacle for the clinical trial. So the clinical trial would be like for 2 to 3 years duration. Like will be the kids, they'll be wearing that special spectacles for 2 to 3 years time, and then we'll be looking at whether the myopia, the power of the eye is progressing or not, whether it's working or not. So that would be the main agenda. So now I'll actually go through all the steps one by one. So first I want to start with the basic research. What was my research about and what was my PhD about? So my PhD was actually, the main topic was myopia or nearsightedness. So I think you guys are aware of nearsightedness. Like you can say it's an eye disease or pathology where the light rays actually focus in front of retina because the eye has a more power, it's stronger. And therefore we can't see the target very clearly. The image is actually blurry. So therefore we need to wear negative lenses in front of the eye. We need to place negative lenses to bring this focus at the retina. So that's the condition called myopia. Now, myopia is a global problem. It's it's one of the 5 immediate priorities for the World Health Organization. Now, one of my friends asked me why you guys are so worried about myopia, because if someone is having script, the eye power, they can go to the doctor and get a glasses, and then they can see things clearly. So what's the big deal about myopia? Why government is putting a lot of money to reduce the myopia progression? So myopia is not only about the vision problem, it's not only the refractive error. The prevalence of myopia has been increasing in actually all over the world, more specifically in the Asian countries like China, Singapore, Hong Kong, Taiwan. And in South Korea, the myopia prevalence can be as high as 96%. So 96 people out of 100 people may wear glasses in South Korea. So the problem with myopia is that that's the characteristics of myopic eye. So this is the MRI of a myopic eye. This is the emmetropic eye. What happens in myopic eye? Myopic eye is actually longer than the emmetropic or the normal eye. So that's the main problem. So it elongates over a period of time. And because of that, what happens? This is called retina. That's the screen behind our eyeball where the image projects. So as the eye elongates over a period of time, there might be a thinning in the retina, and there might be a lot of lesion in the retina, the pathological condition like retinal detachment, glaucoma. That might cause blindness. And a recent report has shown that the global economy losses about 260 billion per year due to the vision impairment, which is mostly related with myopia. So this is a serious problem about the myopia. So there might be several factors on the etiology of myopia. One of the known factors is genetics. So if both of the parents are myopic, definitely there is a high probability that the kids will be myopic. But there are also several environmental factors like the near work education, occupation, lack of outdoor activities. So I was actually mainly focused on the near work activities. Like kids, they do a lot of near work activity, like reading a book or like playing with iPod, Those sort of near work activities may actually increase the myopia progression over a period of time. The another factor could be the downward gaze. That is also quite important for the myopia progression, along with the accommodation of the near work. So accommodation is one mechanism, like when we bring a target close to our face, or when we read like a book, so we accommodate. That is like there is a muscle inside our eyeball that relax, and the lens actually moves backward and forward slightly and focus the target. So that's one mechanism. So when the muscle actually contracting, that may put some pressure on the eyeball, which may elongate the eyeball. So that's one of the mechanical factor. Another mechanical factor is the looking downward gaze. So most of the time, like when we perform any near work activities, like working with computer or reading a book, we generally look down. And when we are looking down, the extraocular muscle, we have a 6 extraocular muscle surrounding our eyeball, and the extraocular muscle, they actually helps to turn our eye in downward gaze direction. So there might be some mechanical tension from the extraocular muscles of the eyeball, and that may elongate the eyeball over a period of time. So those are the two mechanical factors: the muscle tension, like the ciliary muscle tension during accommodation, and the extraocular muscle tension during the downward gaze. That may elongate the eyeball over a period of time. Another factor could be the eyelid pressure. Like when you look down, the eyelid is actually partially, it's coming downward direction, and it presses on the cornea. Cornea is a transparent surface, the outer surface of the eyeball, which is quite flexible. So if you press on the cornea, there will be a depression. So that actually alters the optics of the eye. So those are the biomechanical factors: the lid pressure, gravity, and the extraocular muscle tension that may alter the optics of the eye when you do near work. Now in my experiment, what I have done, I measured the biometrics of the eye. Biometrics means is the physiological dimension of the eye, like the distance. So this is one surface called cornea. This is inside the lens, inside our eyeball, and this is the retina. And the length, the distance from here to here is called the axial length. And in the myopic eye, this length is longer than the metropic, than the normal eye. So what I have done in my experiment, I measured all of the distances, like a component, during the downward gaze and during the near work. So actually we have built a experimental setup. These are the 3 optical instruments that measure the optics of the eye and the biometrics of the eye. We have shifted those instruments on a custom-made tilt and height adjustable table in such a way that we could measure the ocular parameters and the optics in down gaze during the near work activities, during accommodation over a period of time. So this is the experimental setup we used for the experiment, and this is the result. I just want to go through very briefly what I have found. This solid diamonds here shows the changes in the axial length for the different conditions. This is like when we are looking down, just look down, but don't look at the near target, just look down and the distance. This one is just looking like a near target, but in primary gaze, in straight gaze. And this one is looking down and focusing a near target. And we can see when we look down and focusing a near target, there is a dramatic change in the axial length, there is an increase in axial length over a period of time. So if we read a book for 10 minutes time, the axial length starts increasing from the beginning, from the 0 minute time, and gradually it's increasing over a period of time. So it is a small change, like a 20 micron, but the cumulative effect of these short-term changes might lead to cause a permanent damage or permanent axial elongation to cause a myopia progression. So then, based on the results, I was thinking what we can do, how we can solve this problem. The one solution would be if we can bring our target from downward gaze to the primary gaze. If we just look straight and read, that would be one solution. Then we don't use our extraocular muscle to look down. We just hold our target like this. But the problem with that would be like we are very much habituated reading like this. We hold a book like a 40 centimeter distance with a 20-25 degree angle, and it would be really difficult to change our habit, to keep the books like this. So that would be a problem. Then I thought we probably may come up with some special optical device that would help to bring the target from downward angle to the primary gaze. At least can reduce the angle slightly. And only one optical component can do it, and that is prism. I'm sure most of you are very familiar with the optics of prism. It's a very simple optics, like when the light rays go through the prism, it actually bends towards the base. So what happens, the image actually shift towards the apex. So if we hold a base down prism in front of our eye and then we look at it near target in downward gaze, so suppose if we hold a target at 40 degree angle, and if we hold a 20 diopter prism base down, apex up, and then look at the target, then our eyeball don't need to turn 40 degree. Probably 20 degree will be enough, because the image actually comes upward direction, because the image shift towards the apex. So I thought that would be one of the approach we can use. And that might be the treatment option for myopia. Now the issue is, prism is a very known optical component. It's not a novel idea. The novel idea was to put a prism in a particular angle with a component of defocus in a spectacle lens. That would be the novel idea. So now I just want to go through the different myopia treatments available in market. One of the treatment is definitely the atropine. That's a pharmacological agent. So this has a really good response in terms of treating myopia. But there is also a lot of adverse effect of using atropine. That could be actually when you are putting atropine, the ciliary muscle gets relaxed, so the eye is actually getting paralyzed for a long time, and there might be a lot of side effects like cataract and the ocular allergy. So this is not a very successful treatment option for the kids because of the side effect. And there are a lot of other treatment available like spectacle and contact lenses, which can reduce the myopia progression about 30 to 50%. But spectacle would be the most convenient treatment option for the kids, because it has a minimum side effect, because it's a non-invasive method. Whereas using an eye drop or contact lens is invasive because they are touching the eyeball. So spectacle is the most convenient and easy way and less side effect for the kids. So this is a complete design that I actually thought this would be really helpful for the kids to reduce the myopia progression over a period of time. So this is basically a progressive spectacle. We are probably familiar with the progressive spectacle that we use after 40 to 45 years age because of the presbyopia. So what is the characteristic of progressive is it has a gradual increase in the positive power in the corridor. So if we look at a computer, we can see things clear. If we look at a near target, we can see the things clearer. So it has a multifocal points. So we can, wherever we look at the target, we can see things clear. So that's one of the characteristics. Another thing is that's the novel idea, is inducing oblique prism with a different magnitudes along the corridor. So whenever we look at the computer screen, actually probably we need to look with the 20 degree angle, but because of the prism, we probably need to turn with the 10 degree angle. So we reduce the magnitude of the downward angle. And again, when we look at the near target with the 40 degree angle originally, but when you put a prism, we don't need to turn our eyeball for 40 degree angle. Probably 20 degree would be enough. So that way we can reduce the magnitude of the angle for the different near work activity. And also the plus power actually help to reduce the accommodation effects. So that way we can actually reduce the myopia progression over a period of time. That was the main idea of the patent. Now the question was still exists whether this is a novel idea or not. So I have done a lot of literature search and the patent search, and did not find exactly any idea that have done this design. So after you think something is novel, the main idea would be identify whether it's novel or not. So the first thing will be performing the patent search, and then approaching to the supervisors and talk to them. They are more experienced definitely than us. And then propose to the QUT blue box. They are really helpful, knowledgeable, and they know about the patent, so it's really helpful, so we can approach the blue box. And then finally we take legal opinion from the patent attorney, and whether it's a novel idea or not, whether it's patentable or not. Then if it is a novel idea, then we lodge, like QUT, lodge a provisional patent application or the final patent application, depending on the status. And so that was the step actually I followed throughout the journey, like throughout my PhD. And then, like after I lodged the provisional patent application, I had to, as I said, like I had to conduct another experiment to prove our hypothesis, like when we look down and accommodate, and when we are looking in. That's a combination of three factors: convergence, downward angle, and the accommodation, that the axial length is increasing. Because in the previous experiment, I have actually looked at the changes in axial length only in down gaze and accommodation. So the in factor was missing. Because if we think about it, when you read a book, like there are three components. We are looking down, we are accommodating, at the same time we are actually converging our eye. We are moving our eyeball because we are tracking those lines. So that component was missing in my previous experiment. Therefore I had to conduct another experiment. So in that experiment, this setup is quite similar with the previous setup. We used only the optical biometer on a tilting stage, and it's a optical setup. I'm not going into the details. And this is the top view of the setup, side view. So this is a rotational stage that we can rotate subject's head to induce a different angle of convergence and also the downward angle. So this is the near target. Subject was actually watching a video on an iPod screen. So with this setup, we are trying to simulate the condition when the subject is reading, what they do, like they scan the line, they look down, and they accommodate. Those three factors we actually induced in this experimental setup. And we also monitored the head angle using an application with the iPhone. When subject was rotating their head, how much angle they are rotating. So it was controlled with this software. So this is the condition, like the final eye turn is looking down and in and accommodating. So that's the condition we measure axial length of the eye. So these are the different conditions when watching TV, working with computer, reading a book, and we simulate with the different conditions, the different combination of convergence angle and the accommodation, and we measure the axial length. And this is the results. Looks like quite promising. Like this is the condition for the no accommodation, like when we are watching a TV. So watching TV may not be harmful for our eye, whereas working with computer may moderately increase the axial length over a period of time, but definitely reading a book at a close distance, because the kids, they hold a book at a very close distance, about 20 centimeters because of their short arm length, and that condition definitely may increase axial length the greatest amount. And this is a small video clip I can show you that shows. This is not in the human eye, this is in the primate eye and adapted from another publication, but the idea is to show like when we accommodate, the ciliary muscle contract, and this is another part of the eye and which actually goes backward, going backward. So this is another video where we can see the retina. This is the retinal choroidal junction and it's coming forward. So these two video actually shows there is a mechanical effect when we accommodate, when we read. There is a mechanical effect, and due to this mechanical effect, probably the eye elongates over a period of time. So after that, experiment, when we were confirmed that there is some effect, it might work. So then we approached to QUT, and QUT said, that's a good idea, then we can definitely apply the final application. We launched the final application in 2012. So it's still under examination. We got some comments back from the reviewer and the examiner. It looks quite promising so far. So this is the step 5. Like at this stage, we are trying to communicate with the different industrial partner if they are interested in the technique and if they can put some funding and we can do more research. So there are different funding opportunities. One, definitely bluebox offered us a proof of concept funding to conduct more experiment, and there might be some investment from the industry, and there might be another funding opportunity from that is the venture capital funding from MRCF. They are quite interested. So, but we are mainly focused now. We are actually talking with a couple of investment company, and they are showing their interest. So there might be a future collaboration with them for the further development of the product. So the key factor for the research commercialization, I would say, identifying the novel technology is quite important. Then the confidentiality, don't discuss with your friends, just talk to your supervisor and then approach to QUT bluebox. They will protect your idea, they will guide you what to do, and then definitely protecting your IP, apply for the patent, and then communicating with the different industrial partners and for the further development of your technology. Those are the steps, I think. And my experience working with bluebox, definitely I should say it's like patenting the invention is one of the main thing. Like I came up with the idea, but patenting an idea is not that easy. Sometimes it's easy to come up with idea, but patenting an idea is very difficult, and bluebox know how to do it in the right way. So that's the one important thing. And dealing with the patent law, I still don't understand the law very well, to be honest. I just deal with the science. And it's very, very complicated. Anthony is the best person. If you have any question, ask Anthony. And definitely periodical meetings with the research team is quite important. Financial support, bluebox offered us some financial support. And communicating with the potential industry partner. bluebox is doing that. And definitely most of the staff in bluebox, they are very, very helpful, very approachable. So finally, I would like to thank my research team for the support. Thank you.
Yes, just a quick question. Balancing the expectations